I just wanted to thank the organizers because this is really a very, very interesting workshop, and I'm happy to be here. And I will not talk exactly about what I wrote in the abstract because I realized it was not possible in 25 minutes, and also try to adapt a little bit to the audience. So I'm a member of the Palaiseau Theoretical Spectroscopy Group, and in particular, the work which I present here has contributions from Jarkko Koskelo, who is now working for Nokia, Ayub Awina, who is now in Bochum, and Matteo Gatti, who is my friend and colleague in Palaiseau. And I will give quite a long introduction about what we would like to do, because I'm not from your community. And what we would like to do is a sort of Lego playing. And I will put this in relation to perturbation theory. And I will also remind you about the link to other people who are playing in this field. And then I will concentrate on the homogeneous electron gas and show you a few things which I hope are interesting for you in the homogeneous electron gas. So what we would like to do is to break down the many-body problem. We in Palaiseau are working on real materials, not the Hubbard model, only sometimes. And so we have the double problem of interaction and the fact that the real material is quite complex. And this double complexity means that we have a problem of ecology, I mean, needing to do very large calculations, and also of understanding, because just getting numbers, just crunching numbers doesn't tell you anything. And so what would be great if we could extract universal pieces from this problem, and that we could do once and forever, do big calculations just once and forever, store the result, share it with other people, and then use it all over and over again for all kinds of materials. And this is really like playing Lego. If you think of the many-body Schrödinger equation, for example, with all the different particles, it's like playing Lego when I was a child. You had these small Lego pieces, and if you wanted to do a complex construction, it took a lot of time. And today, the children have prefabricated pieces, and this is, of course, then like having, for example, a spectral function here and seeing, oh, there are some building blocks that are always the same. And this would make constructions much faster and also give you better understanding, because just you have to understand what is in these universal pieces and how to put them together. So what does this have to do with perturbation theory? Actually, perturbation theory is basically a Taylor expansion, right? So you have a function f of x, and you know them in some points a, and maybe also the derivative and so on. And like, for example, many-body perturbation theories of Taylor expansion in a vector. Okay, so the link is here that if you know these points A, these are your building blocks, then the Taylor expansion tells you how to reconstruct the function everywhere. So our building blocks would be the function in the point A, maybe its first derivative, maybe its second derivative, and this would be our Lego blocks, and this we could store. Now, in many-body perturbation theory, we do this expansion with respect to the Coulomb interaction. Here I've written the expansion in terms of the Baire-Coulomb interaction, and this expansion has several problems for what concerns our project. So first of all, we know that this thing doesn't necessarily behave very well, convergence-wise. And we, of course, never do really the Baire expansion. For example, we in the solid state expand rather in a screen Coulomb interaction. And this is very important because we sort of use Dyson equations for quantities like the polarizability or so to sum up an infinite class of a class of diagrams to infinity. And this makes our expansion, of course, much better behave. Still, I think this way of doing perturbation theory, although I have done it all my life, is actually too basic because we don't optimize it at all. We just straightforwardly expand besides the Dyson equation, and we come back to this later. And the most difficult point for our project is that we actually expand exactly in the quantity that is universal in the Coulomb interaction. And that means that when we go to materials, so for every material, we have, for example, to calculate this derivative, which would just be a Green's function, for example, right? We have to recalculate it for every material. So there is nothing that we can store and give to other people. And therefore, expanding exactly in the quantity that is universal is not a good idea for our project. Before coming back to this, let me just say, remind you, as I just said, so this is, of course, an expansion in functions. So this can be seen as a vector. So what we really do is a function as a function of a vector that we then expand. Okay, so what we would like to have is that this A vector now is some universal points that where we can have the function and we can store. For example, it could be something that I would call homogeneous. So a vector where all components are the same. Then I have just a number that describes this vector. And then I could maybe for all these homogeneous vectors store the result of the function and maybe its first derivative and so on. And then I could expand in the materials dependent ingredients. For example, in the density, in the external potential, and so on. And this is actually something that is used in the context of density functional theory. Even Kohn and Sham have proposed expansions in the density. We have also worked on this. And so in the density functional framework, this is actually quite common. But it's not so in the many-body perturbation theory framework. And then there's another thing which you know about perturbation theory. Of course, you want to optimize it because you never do, besides maybe when you do diagrammatic quantum Monte Carlo, you don't do perturbation theory with the idea that you will go to infinite order. You do perturbation theory because you think that your first order or your second order are already very good and you stop there, right? If it doesn't work, you switch method. Okay, that means that you have an interest of making this first order very, very good. And in fact, you know from Taylor's theorem, from the work of Cauchy and Lagrange and so on, that you can actually carefully choose, for example, the point where you take the derivative. It doesn't have to be A. You carefully choose this point, and then you can make even the first order exact. And for example, if you have a quadratic function of a vector, this one, with some parameters alpha, beta, and gamma, if you just choose the midpoint between A and X, then the first order gives you the exact result. And that is something that we do not at all exploit in many-body perturbation theory. It's clear that it has a problem because this midpoint, suppose you only know the result for homogeneous vectors. So if A is homogeneous, usually your real system X is not homogeneous, so the midpoint is not homogeneous. But since this is actually a function of a vector, and this means that you have to solve this kind of equation, okay? You have many more than one solutions, so you can actually find a homogeneous point where the solution is also exact. And that means that if you have a clever way to choose these points, you can store your Lego pieces, so you can choose your function, the zero order, you can calculate your derivatives in this homogeneous point, and you can store them and then reconstruct a very good approximation to this Taylor expansion. Okay? Because of this fact that we have a function of a vector, and as I have shown you in first order, we have many solutions, we actually already have many solutions to zero order. So it turns out that in many cases, even the zero order can be made exact. So if you have a function of a vector, it could be that this has the same value as a function of a different homogeneous vector. And that is something that we are exploiting now very much, is essentially in the framework of density functional theory, but not only. And the way to find this homogeneous vector that gives you the good or even exact result of our function, we call this a connector, because this connects a real system to some homogeneous model system. So for example, we do this for the exchange correlation functional exchange correlation potential of the Kohn-Sham theory, which we take from the homogeneous electron gas. So these are our Lego pieces that we have to calculate and to store. So I even found a actually prefabricated scientist, see? Okay, so the idea is to import Lego pieces, for example, from a homogeneous system. And this can be done in principle under certain conditions exactly. And in practice, we have ways to design good approximations. Okay, of course, this is not a completely original thing. If you think about it, especially in density functional theory, you have the exchange correlation potential as a function of the density. Many people use the local density approximation, where you simply replace this density of the real system with a homogeneous density that equals the local density. This is so in this framework, a rough approximation to the connector, right? And it uses the principle of nearsightedness. It says, oh, only this point is important actually where you look, so I can flatten out the rest of the density. In dynamical mean field theory, in the single site approximation, you do right the same. You have your local self-energy, and you say it just depends on the Green's function site locally, right? It's the same idea of nearsightedness. Simply the model is different. You take it from the Anderson impurity model, but the principle is right the same. So both are based on this idea of nearsightedness, And in this work, if you're interested, we try to go beyond this intuitive idea and to make this approximation systematic. So to have the best choice, for example, for this density, which is not the local density, but a systematically designed choice. And just to give you an example, this is bulk silicon. I know that you couldn't care less for silicon, but for us, it's a very important example. So Ayub did this. This is the density of silicon along a certain path in the unit cell. Okay, just simple the density. And it's actually calculated by auxiliary field quantum Monte Carlo. We have a collaboration with the group of Xibei Zhang on this. And then here you have the errors of different functionals of DFT. Maybe we could look here. So for example, the LDA, which I have just been talking about, gives you a density that has these large red oscillations. If you look at the percentage error, it's about 5% error, order of magnitude. And if we took our design principle to have the best local density, the best homogeneous density, so the best zero order to this expansion, then we get the black curve, which is here. So we see it's much, much closer to the quantum Monte Carlo error bar, which is the gray lines here. And down here in the error, you see we are good. We are actually even better than PBE. So you can design these connections between the model system and the real system in a systematic way and get really, really improvement with respect to either straightforward expansions or standard intuitive functionals. Now, the homogeneous electron gas is, of course, a relatively good model for silicon, even though silicon is already quite inhomogeneous, but it's certainly not a Mott insulator. But we have this parameter-free connection and a systematic route. So this is a promising route for us to build Lego pieces from the homogeneous electron gas. And these are pieces that actually can be calculated once forever, interpolated, and stored. Different models are possible. This sort of framework does allow to use any model. The homogeneous electron gas has the advantage that it's very universal. So it doesn't ask, for example, where are my atoms, right? You could, for example, think to make a model where the atom potentials are much, much simplified, but you would still have, for every sort of crystal structure, you would have your model. The homogeneous electron gas is very universal. It's easily storable because it's numbers. And so for now, it's our model. We are working on other models. It's important to go to other models, especially for the correlated system, but this is our model. And therefore, I would like to talk about the homogeneous electron gas, because what you need when you use such a model approach is you need your model over a wide parameter range, right? Because you would have to simulate your real system, so you need, the model has to be very flexible. So we need it over a wide parameter range, not just at the density of silicon or the density of sodium or whatsoever. And then we found that this is actually very interesting. There are many interesting things in the homogeneous electron gas. And especially if you come from the Hubbard model, I would like to convince you that the homogeneous electron gas is also interesting and has many parallels, especially at low density. For example, many, many years ago already, people have started to talk about the appearance of ghost plasmons or excitonic collective modes. And I would in particular like to refer to the work of Takada. There are several papers by Takada, very, very interesting, but also people before, like this work of Takeyanagi and Liparini and many others. Okay, so they said there are sort of exotic excitations in this electron gas. So if you look at the electron gas excitations, of course, you have your particle-hole continuum, you have the well-known collective mode, which is the plasmon, and then decays in the particle-hole continuum. We ask ourselves much less what could be on the other side. For example, could there be, at large wave vector, another collective mode that maybe comes out of the continuum? So what are these ghost excitations, and are they important at all? Okay, so let us think about the quantities we use. Our key quantity is the inverse dielectric function that screens an external potential to give you the total potential in linear response. And you can build this inverse dielectric function from the density-density response function and the Baer-Coulomb interaction. Now, if you make a model for the density-density response function that has just one dominant pole, omega p, okay, this would be a reasonable model. Then you can, of course, immediately write down the inverse dielectric function is 1 plus Coulomb interaction times this chi, and you can look at it at omega equals 0, and this is your expression. Now you see that this expression is positive, and now we can look at this drawing that I made here as a function of this pole. starting from the pole very far away and going down to 0, and maybe minus infinity if you want. Okay, so it's the red curve. So if the pole is far away, there's no screening. Epsilon minus 1 is 1. And as we come closer, there is screening. The thing becomes more and more negative, and then it crosses 0. And it goes down to minus infinity. So you get negative inverse dielectric function. Okay, now from this, you can calculate the dielectric function and just invert this expression. Okay, gives this one. And you can write it, as we usually do, as 1 minus Coulomb interaction times the irreducible polarizability. And you can look at the poles of this P, and you will find that is plus and minus a square root. And right at the point where the screening becomes negative, the argument of the square root becomes negative, and the poles split into a pair of complex poles. And this is called an exceptional point. Okay, so if we have a low energy excitation, we can have negative screening. The poles of the irreducible polarizability will move to 0. Is actually the green curve is the dielectric function. So when this goes down, when the inverse dielectric function goes down, dielectric function goes up, and then it goes to infinity, comes back from minus infinity, and then we come into the unstable regime. Okay, so this means that actually this happening here is a precursor to the instability. And for this, it's very important. Then we can say, okay, but what kind of excitation is that makes this effect? So is it really an exciton? Is it an excitonic collective mode? And when we talk about excitons, our ears go up because we are excitonic people, okay? And so this is the work of Jaakko Koskelo. And we say, okay, let's solve the Bethe-Salpeter equation in the homogeneous electron gas. How does this work? Of course, we have standard approximations. We usually do this in a GW approximation. So we take some pre-calculated dielectric function, for example, in the RPA, typically, this is our epsilon in. We set up a GW self-energy, and this is the electron-electron interaction, and this gives us band structure, spectral functions, and also it gives us the electron-hole interaction of the Bethe-Salpeter equation, and this gives us then a new dielectric function. Now, if the electron-electron, if the dielectric screening is very strong, and you would think in a metal, in homogeneous electron gas, it's infinite, then all these interactions are gone. So you cannot have an excitonic effect if you think about the infinite screening of a metal. But of course, even in a metal, screening is infinite only at infinite distances. It's a macroscopic screening. The closer you come, the less you screen. And here I show you actually the RPA screened interaction. It's minus W, it's the electron hole attraction. It's the blue curve here as a function of distance from an external charge, okay? So you see that actually at infinity, of course, it's 0, but then you have a region shaded here where it becomes attractive and actually very strong if you go to 0 distance. So it could be that this RPA screen interaction is strong enough to make exciton binding even in a metal. So what we did is we solved our Bethe-Salpeter equation with this RPA input, and we calculated collective modes. These are determined as the zeros of the real part of the dielectric function, okay? These are the collective modes, and they're plotted here as a function of wave vector. And what you see is the blue curve that we obtain, and there's absolutely no low energy mode. This is just the standard plasmon. This is at RS equal 22, so it's already very low density. Now you could say, okay, but you went in with an RPA screening. Okay, you can do better. Of course, we can do better, right? So we took actually the, no, first of all, let me compare this. This is actually the result of pure RPA, no Bethe-Salpeter equation, pure RPA, no electron hole interaction. You see it's very similar, okay? So if you suspect that this is the problem of RPA screening, then you just take the exact static screening of the gas calculated by Monte Carlo, and you plug it in your Bethe-Salpeter. I should say that we always do an approximation of instantaneous interaction in this Bethe-Salpeter, so a static screening, okay? So this exact static screening from Quantum Monte Carlo by Moroni, Seppali, and Senatore is the black curve here. You say it also, of course, screens infinitely at infinite distances, and it's actually even has a smaller region of being attractive than the RPA interaction. Huh? It's stronger, the screening is stronger, and we know this. So this is no good, and in fact, no collective modes, believe me. Okay, so now the approximation we actually did, if we think about it, this is the Bethe-Salpeter equation where you have propagating electrons and holes and an electron-hole interaction, which is determined by the derivative of the self-energy, and we use GW as input usually. So we have to be better here. Okay, so this is the GW approximation. You have a self-energy, which is a Green's function, and interaction, which is screened by the density-density response function, and then you have a vertex. And in GW, we replace this thing here just by a Berg-Coulomb interaction. Okay, so what we have to do is to sort of simulate this vertex. Okay, it's very difficult, and we know that we cannot do this at least to many orders. And so what we do is we borrow from other theories. That's another very important ingredient. So what we do is, in this derivative, we approximate the self-energy by the Kohn-Sham exchange correlation functional. Okay. Actually, if you go to very small distances, this is even justified, because then the more you are local, the more the things actually, you can find a link. And if you look at the calculation of a total correlation energy, this can even be exact. Okay, it's an approximation for spectra, but it's our approximation, and we use the adiabatic local density approximation here. And we redo, first of all, our effective interaction. So if you do this with this vertex, you have no longer the interaction between classical charges. You have the interaction between a classical charge and a fermion, and this is what you need. You need interactions that are felt by fermions. You need induced exchange correlation fields, not only induced Hartree fields. So this is called a test charge, test electron dielectric function, and it's the red curve here. And you see, of course, infinite macroscopic screening, but a very large range of strongly attractive interaction at short distances. And indeed, plugged in the Bethe-Salpeter equation, this gives us, first of all, a modification of the plasmon dispersion here. We actually get a negative plasmon dispersion. We know this is correct for the low energy, low density gas. And then a brutal turning around and shooting down to a low energy collective mode. So this is exactly what we hope to find. Okay, if you now look and think, is this correct? So the only thing we can actually compare is static screening, because we have it from Monte Carlo. So the output static screening now. So at RS equals 4, density of sodium, static screening here as a function of wave vector is just starting from 0 and then you go up to 1. This is very boring. If you go to RS22, you find negative static screening. The black result is the quantum Monte Carlo, goes down very negative and comes up, goes to 1, okay? And here you have our different approximations. So the standard Bethe-Salpeter in blue, the RPA in green, and this new result here in red. And you see that even though it's not strong enough, we are correct at large Q, we are correct at small q, and we have the qualitative appearance of the negative static screening. So we think that we are qualitatively correct. Okay, now we can look at the wave functions, the electron hole wave functions, because we have the Bethe-Salpeter equation, which we can write as a two-particle problem. So we have an electron hole Hamiltonian and electron hole wave functions. And if we have an exciton, we will have strong correlation between the electron and the hole. So the electron wants to stay around the hole. So let us first look at these ghost poles, the poles of P, the complex poles. They always appear in pairs. And this is the wave function of these complex poles. You see this pair, each of them breaks symmetry. So here we have the Q vector that goes in this direction, okay? And you see that you have a little shift to the left here and a little shift to the right here. It breaks the symmetry, but the two together conserve symmetry. And if you look at this pattern, you will find it looks very similar to a plasmon. So even though it's a pole of a different quantity, the electron hole wave function looks very similar, which maybe justifies why people call it a ghost plasmon. Okay. Also at larger wave vector, we have this similarity. If we now look at the low energy collective mode, the pole of chi, the thing that you would be able to measure actually, for example, in inelastic X-ray scattering, this is its wave function. So in the left picture, we have the Q perpendicular to the plane, and you have some localization around this Q. And here the Q goes in the XZ plane in this direction. And what you see is that the electron can be far from the hole in direction of Q, but it's very localized close to the hole in the other two directions. So it's a very anisotropic electron hole correlation that we have here. So with this, I've talked about these ghost and low energy modes in the low density homogeneous electron gas, and I've shown you that in the Bethe-Salpeter equation, if we put vertex corrections, and I tend to stress that we take them from another theory, we try to combine theories in order to make it non-perturbative, we find an effective weakening of screening at short distances, as one would expect. And our effect is not strong enough, but we know that besides the fact that we have short distances, we also have to care about time. As I told you, we have made here an instantaneous approximation on the interaction, whereas in reality, it takes time to build up a screening cloud. So we think that we still overestimate screening. And so we have to move to a dynamical Bethe-Salpeter equation, which is on the way. And in conclusion, we would like to play Lego, and we care very much about the fact that we should try as a community to work once, do the big calculation once and forever, as Sepperle and Alder have done for the electron gas. And this is the reason why DFT calculations are considered to be so efficient, because we take calculations that have been done once and forever. We should store them and we should share them. And perturbation theory, I think, can be optimized. I think our Manybody perturbation theory does not yet take into account all the things we could do. I think we can do much better. And especially if we look at other fields like density functional theory, we can really learn a lot. And we can push the fact that we recycle data from models. It could be an alternative or even combined with machine learning. But I think it could be, in part, replace the fact that now people are moving to brute force machine learning on real systems. I think we can learn a lot from models and recycle it for real systems. And the homogeneous electron gas, even though we want to explore other models, stays an important ingredient for us. It has interesting exchange correlation effects. And yeah, it will not be the only model, but it's very important. And in conclusion, I think we should just play together. Thank you.